Hello everyone. So today I am going to discuss about TurtleBot3 simulations using Gazebo, and I will be using ROS to Humble for this. So let's go through it. I will also explain the script I have written for the control. So first I am going to launch this Gazebo with the empty world.launch.py. So you can get these files from ROS Gazebo documentations. So you can see that this is the empty world, and I have spawned this WafflePie robot in Gazebo. So now what I am going to do, I am going to start my script. So now my script will ask the goal x coordinates. So I will give, for example, 2, and it will ask the goal y coordinate. For example, I will give 1. So as soon as I started, my robot will start to move and it will go to that position. You can see that it's moving, and I am also displaying the distance from goal, as you can see here. So it will try to move as the distance to the goal is decreasing, so the speed of the robot is also decreasing to achieve high accuracy. As I have given a very high tolerance, therefore it is taking a lot of time. So while explaining the code, I will tell you. So now you can see here the message came, reach the goal, and control loop is ended. So now I am going to explain you a bit about how the code is working. So this is the Python script for this control. So this is the basic publisher and subscriber node. So I am publishing to CMD well, that is the topic taken by Gazebo WafflePie, and this is the ODOM topic through which I will be reading the current positions of TurtleBot3. So I have used threads here for the inputs, but you can just ignore them and do directly also. Directly also it will work. So this is the set goal post. So we will be asking the coordinates from user. So these are the basic ROS functions like post, callback. So this is the main function where we'll be calculating the error angle, and this is the calculate distance. These two are the main functions. So through this we are returning the angle, we are returning the distance from the goal. So you can see that we are reading the current positions and where we have to go, and we are subtracting this. So I have used Euclidean distance, that is kind of L2 norm for the distance. You can use some other also, like if you can always try and test some other thing. For the error angle, now this is important. For the error, I have used quaternions, and I have converted quaternion to rotation matrix. So you can try different things here, like you can directly use angles. You can directly, with the help of angles, you can directly make rotation matrix. But if you do that, you will find some difficulties. So try that and try to find out what kind of difficulties you will fail, and what are the benefits of using these quaternions to convert them to rotation matrices. So once I know that what is my desired rotation matrix, means where we have to go, and this is my current rotation matrix. So what I will do, I will just take a dot product of these two. So try to search why I have taken the dot product. So this is the basic mathematical concept, and through this I have just find the error angle. So this is the main calculation for angle, and this is for distance. Now going through the main control loop. So this is the main control loop. Now various things are here. Like if you see, I have given the linear velocity in x direction and angular velocity in z direction. That is like very obvious. So I have done that. But these 0.2 and 0.6, these are the control parameters. That is k. So I found it through hit and trial method. You can also try some other methods, like you can also try some other values for this k and see that whether it is reaching the goal faster or it is taking more time. You can also change this tolerance. So I have taken a tolerance of 0.0003. So you can use some different tolerance and like see how fast it is going there. And one thing, like if my if you can, I am calculating the angle from the goal position, like what angle is required. So if it is coming in this values, then I am stopping it. So why I have done this, like if I will not do it, what will happen? So I have faced some difficulties, therefore I have done this. So like you can just try these. I am just giving you a basic idea that what are the things I have done. So you can just tweak with them. I will also provide you this code. So you can tweak different things and try different things and see what will happen. So as we reach to the motion, like we reach to the goal. When this distance is below this, then what we will give? We will give 0, 0 velocity, angular and linear, and we will stop. And these are the basic ROS 2 things, spin ones, and these you may be knowing. And I have used some signal handlers because I am using these thread things. Thus you can ignore these things like if you want, and you can first directly try without threading and then see what difficulties you face. Then you will get to know why I have used these threads. And this is the main function, the control loop. So this is the basic. If you go to the logic, so logic is very simple. Logic is this one, the angle one, and then this one. This is the distance one. So you can just play with them, and these are the control parameters. Just try to play with them and see what are the difficulties are there in this. I will also provide the GitHub link for this code that you can find in the description box. So again, like if you want to go to some other position, so we can also try that one more time. Like if I want to come back to my home position, that is 0, 0. See how is it coming. See, it is reaching close to the goal position very quickly, but as soon as the distance is decreasing, the speed will reduce. Because I have taken this velocity, like I am giving the velocity as a function of distance from goal. So therefore, as the distance is decreasing, the velocity is also decreasing. And I have used a tolerance of 10 to the power minus 3. So therefore, it is taking a lot of time. You can see that still it is rotating about its z-axis to just try to go as close to the goal as possible. Now you can see this, we have reached the goal and control loop ended. So this is the basic thing, like you can take and build it from here. So thank you.